Hi, let us talk about torsion. Torsion is a type of internal force causing a member to twist along its principal axis. It happens when there are torsional moments acting onto the member in the opposite direction, happening at different places of the member. This torsional moment causes shear stress in the member, and this shear stress will lead to principal tensile stress inclined at the angle of 45 degrees to the member's axis. Taking this member as an example, this is its central axis. When there is a torsional force, the member tends to twist in the directions of the force. This leads to tensile stress within the member, and when this tensile stress exceeds the concrete tensile strength, diagonal torsional cracks happens. The crack will look something like this, spiraling around the members. This kind of force can happen within a member in reinforced concrete structures. Now you might be curious, what are the circumstances that can lead to torsions within the structural element of a structure? Let me share with you a few examples so that you can imagine how torsions occurs. Torsional force can happen within the column, the wall, and even beams, depending on the circumstances. Taking this as an example, let's say this is the key plane of the structure. You want the structure to be a braced structure. That means you need mechanism to resist the lateral load. Let's say this is a high-rise building. High-rise building, you have concern with the wing loads acting laterally to the structure. To make it a braced structure, you need members with strong resistance to the lateral loads. For example, shear wall or core walls. With the assistance of the shear wall or core walls, you may design the columns as a braced member, which it will be more economical and easier to design. Now you need to know that this wing load is actually variable actions, which can be there and can be not there. The magnitude and the directions can differ under different circumstances. Now, in the case that you have inconsistent wing load acting onto the structure, the deformations of the global structure may undergo slight twist. This will require torsional resistance within the core wall, and the relevant columns may also be subjected to torsional forces. Now, if you strategically place the shear wall somewhere here, the resistance can be contributed by this shear wall. This will minimize the torsional effects onto the structural element. This gives us an idea how do you arrange the structure would influence the response of the structure. One more thing about the applications of the wall members. We are talking about the load-bearing wall. In the design, typically we assume that when subjected to the horizontal force, the wall member will deform in one single axis. This is only valid when you are combining the wall in two different perpendicular directions. Imagine you don't have this, and you have the shear wall to resist the force alone. Very likely it will end up to be something like this, as the deformations tends to go to a weaker direction. This leads to torsional response of the member. Of course, torsional can also happen due to the ground movement. For example, during the earthquake, when the ground movement is in the torsional directions under the accelerated rate, the inertia of the building would resist the initial movement. This can lead to a twist in terms of the global structure. This is another example due to the ground motion. Another common example where you see torsional happens, particularly in column, is the advertisement board. Normally you see these structures along the highway, quite heavily reinforced, and there is a plain surface here where you can put the advertisement. Because of the plain surface here, wind load can add onto the plank, especially when it is placed unsymmetrically. The wind load can lead to a twist onto the steel pole here. Now this column is subjected to torsion. How about precast concrete structure? You know that precast concrete structures involve prefabricating the structural element in the factory, transport them to the site, and then install them one by one at the construction site. If you observe this beam here, you have the hollow core slab only on one side. This beam is subjected to torsional force, as there are no forces on the other side to counteract the vertical force due to the hollow core slab. Bear in mind that when you do the analysis of the load, the way the loads are being distributed, for the precast concrete structures, it will be different from reinforced concrete structure. For reinforced concrete structures, the loads acting onto the slab can be transferred to all four adjacent beams. However, for the precast concrete structure, the members are typically simply supported. Let's say for this case, the force it will be distributed both sides, leading to vertical force acting along the beam here. Now this member can be subjected to torsional force. Besides that, even if you have slabs from both sides, torsion can also happen within the beam. This is something interesting about precast concrete structure design. For a typical reinforced concrete design, we only design for one stage. That means at the service stage. We analyze the load based on the functions of the building when the building is put into service. However, when you design for the precast concrete structure, you need to design the members in two stages. During the construction stage and also during the service state. Normally, we have no issue with the service stage, but we might miss the construction stage. Let me give you a scenario. You know, in a typical precast concrete structure construction process, you need a crane to lift the member and then install them one by one. That means the loads being acting onto structural elements is very much dependent on the construction process. Taking this as an example, you see the slab from the other side has already done installation, whereas the slab on this side still in progress. Imagine the loads taken by this stretch of the member. You have load on one side, but you don't have the load on the other side yet. This leads to torsional force. Of course, in this case, you have propping to support. What if we are using this beam? Then you will need to design this beam here so that it has sufficient torsional resistance to temporarily resist the torsional force when you are first installing one side of the member. Later, when you have hollow core slab on the other side, then the torsional force being balanced. These are some other examples when torsions can happen, especially on the HB, where it is used to support the loads from the incoming members. Now, if your structures is meant for the traffic users, you might need to simulate the situations where one side with traffic loading while the other side without it. This can simulate the critical torsional load. How about for reinforced concrete structure? There are also many circumstances where torsions can happen. For example, you have a beam attached to a cantilever member. Due to the loading here, there will be torsional moment. This one also, due to the cantilever members here, the beam here is subjected to a torsional load. Or if you have a cantilever here, torsional can happen. Or something like this. Due to the loading from the slab and the deformations of the slab, especially when the span between the beams are relatively large, and when the loadings are relatively large also, torsion can also happen. It may also happen within the curved beam here, when the load is subjected to the curved beam, as the loadings is of a distance from the central axis of this section. This leads to a twist onto the cross-section here, resulting torsional forces onto the cross-section. What you see here, there are many circumstances where torsional can happen. And there is a need to design for the torsional resistance in order to reinforce the member and control the torsional crack.